Okay, so if you go back to what we had done last week, okay, we first had these kinematical considerations about the pressure and energy relationship, and after that we started looking at the internal structure, because up to this point we just assumed that our systems are made up of point particles, mainly ideal gas point particles without internal structure. So what are the modifications when we do take into account the internal structure? And we said that, okay, since we are looking at the internal structure, the effects of the internal structure, let's just first ignore treat the translational degrees of freedom as classical. That is that is for when this coefficient over here is much larger than 1. So in this approximation, the partition function of the n-particle system can be written in terms of the partition function of a single particle system. And that single particle system was a sum over the single particle states. And now the energy has two parts, one the translational part and then the internal part. And the translational part we can just treat as just replacing that summation by an integration over the momentum and position. And then we had this is not n, this is 1. Then the single particle partition function we could write as a factor due to the translational degrees of freedom, that is that v over lambda cubed. And then some function that depends only on the temperature, which was just some of the internal partition function essentially. And then we were looking at what happens what are the modifications due to this internal temperature, internal partition function. And well, we are mainly interested in what happens to the various thermodynamic properties like the entropy, the internal energy, and the specific heat. And then we just first obtain these relations of these thermodynamic properties in terms of this internal partition function. Well, these are all contributions due to the internal degrees of freedom. These are the contributions. So they can be zero, they can be non-zero. And then we started looking at what happens in the monatomic case. Now, in general, if you consider a given system, let's say some molecule, you have the nuclear motion plus the electronic motion. And they are interacting to some extent. But let's say to lowest order, for example, most condensed matter simulations, what they do is they just look at the nuclears, they treat them as if they are moving, they are interacting with each other, and then average electronic cloud. They just study what the nuclear motion is, and then modify the electronic cloud due to the changes in the nuclear structure. So it's just this iterative process. Let's say you start from some initial condition, then treat the electrons as some kind of a cloud, assume the nucleons are moving within this cloud. When the nucleons they change their position, you fix the nuclei and calculate how the electrons move, because basically since the electrons are moving much faster than the nuclei, the speed of the electrons is not that small from the speed of light, by the way. So you have the electrons moving so fast, they will follow the motion of the nuclei. And then we said, okay, so in general, the internal partition function will be the product of the electronic, nuclear, rotational, and vibrational contributions, because the energy will be the sum of those. And then we were looking at various contributions from the electrons. In the case of the monatomic systems, there's no nuclear kinetic energy, that is only the translational motion. And there's no rotations, or there's no vibrations, let's say. Rotations, the atom can have a definite angular momentum or not. So we looked at various cases. In most cases, let's say if L is 0, if both the angular momentum and the spin is 0, then the electronic energy levels will be degenerate. But there is a single state, essentially. If the spin is non-zero, but there is a finite angular momentum, well, the same would hold more or less if there is a total spin 0 and the angular momentum is non-zero, there will be a degeneracy. And the most kind of interesting case, let's say, when both of them are non-zero. You see, if both of them are non-zero, what would happen is that we'll get spin-orbit coupling. And so the energy levels will be split. And this splitting will not be negligible compared to the KT. So this KT corresponds to typically something around 100 Kelvin. That is not negligible even at room temperature. So we need to take that into account somehow. Well, we had looked at various limiting cases when KT was larger than most of these splittings, and in that case we could just ignore those splittings, and we have a 2s plus 1 spin configurations, 2l plus 1 orbital angular momentum configurations, and the sum is just the product of the two. That is the number of microstates. And when KT can be much smaller than that splitting, in that case only the smallest splitting will contribute. So you can calculate how much it will contribute to the specific heat. Well, it doesn't contribute to the specific heat, basically, how much it contributes to the energy, etc. And you see, so basically at large temperatures, since this term over here does not contribute to the specific heat, there's no, the specific heat will be just this translational degrees of contribution from the translational motion, 3nk over 2. At small temperatures, this is at small temperatures. At large temperatures, still there is no contribution because this partition function is just an overall constant. To calculate the specific heat, you just take its logarithm and derivatives, but derivatives is just 0. So this just tells us that if you could study the specific heat in detail as a function of temperature, we should see some peak. And the position of this peak will just let us know what is the typical splitting due to the spin-orbit coupling. So this is basically what we had done last week. Now, any questions? Now we will continue from here. So you see, that was the description for the monatomic systems. We don't need to take into account the nuclear motion, which includes the rotations of the nuclei and the vibrational motion. But now let's look at what are the modifications when we do take into account the nuclear motion. Let's look at diatomic. In this case also we will consider two different cases. What we mean by heteroatomic molecules is, for example, nitrogen monoxide. There are two atoms making this molecule, but they are of different type, or carbon monoxide. When we talk about monatomic molecules, what we will be meaning it will be, for example, H2, O2, deuterium-2. That the molecule, atoms making the molecule is of the same type. Now, the distinction in these two cases is, for example, if you look at the hydrogen, the nucleus of the hydrogen is proton, which is a fermion. But since it's a fermion, this two-proton system, the wave function of this two-proton system should be antisymmetric. Or if you look at deuterium, D2, the nuclei are made up of the proton and neutron, each one of them, and their spin is 1. They are bosons, so their total wave function, by total wave function I mean let's say if we take into account the rotations plus the spin wave functions should be symmetric. So that is what we need to take into account in these monatomic molecules. Now let's look at the heteroatomic molecules first. Now we have the internal partition function will be electronic, nuclear, rotational, and vibrational. Now when we look at the electronics, well, most of the time, again, in this case also S is equal to 0, L is equal to 0, so this is just 1. Sorry, 0. So there's no contribution from the electronic orbit, electronic motion. But still, there will be cases when S and L, they might be non-zero, there will be spin-orbit couplings, and there will be some separation of the energy levels. So if you would take, let's say, one of these states, then the electronic partition function will be just, let's say, G0 plus G1 e to power minus delta over KT. If we just take the lowest energy state, the ground state plus the lowest energy, well, we can just go back and calculate the corresponding specific heat. Well, this is the specific heat. Logarithm of J is just G0 logarithm of G0 plus G1 e to power minus delta over KT. And if you take the derivative with respect to temperature of this logarithm of J, well, the derivative of the upper part, which is G1 e to power minus delta over KT multiplied by delta over KT squared, we need to multiply this by T squared and take its derivative once more. Now let me just take the derivative straight away. Well, let me rewrite this in a slightly different form. This is delta G1 over K divided by e to the power delta over KT times G0 plus G1. This will make the derivative easier. So if I just take the derivative of this one, I have G1 over K times delta times minus 1 over e to the power delta over KT, G0 plus G1 squared times the derivative of this term, which is G0 e to the power delta over KT times minus delta over KT squared. Well, again, let me just do some simplifications. Let's say this minus will cancel this minus, so I have NK G1 over G1 G0 over G1 G0 delta over KT squared. I have delta squared here, and then 1k over here, another one over there, and then I have times over e to the power delta over KT, G0 plus G1 times G0 plus G1 times e to the power minus delta over KT. This is due to the, again, I repeat, due to the only the electronic degrees of freedom. Now we we can look straight away how it behaves for large temperature and small temperature. Now, if you go to the large temperature limit, all these exponential factors become 1. So this factor over here is a finite number in the large temperature limit, but then I have this 1 over t squared, so it goes to 0 in the large temperature limit. Now, what happens at the small t limit? Well, let's see, delta is a positive number. As t goes to very small values, this delta over kt becomes infinitely large. So this exponent just becomes 0, but this factor is just a finite number, but this term over here just becomes infinite. Okay, this term also becomes infinite, but this factor, the underlying factor, goes to 0 exponentially. So basically it again goes to 0. Well, this is in fact a general property of in thermodynamical systems that t goes to 0, specific heat has to go to 0. That is due to the third law of thermodynamics. So again we have this behavior. Well, this is in fact what we had kind of claimed in the case of the monatomic systems. We said that, okay, in the large temperature limit it goes to 0, in the small temperature limit it goes to 0, it has to have some kind of a peak somewhere. Okay, this is the electronic motion. Now let's look at the vibrational motion.
How much is that really goes to 0?
In which limit?
In t goes to 0 limit.
Well, let's say t goes to 0. Do you agree that e to the power minus delta over kt, as t goes to 0, this goes to 0? E to the power delta over kt goes to infinity. So Cv at large temperature limit, at small temperature limit, will be proportional to delta over kt squared times e to the power minus delta over kt. This goes to 0. This diverges, I agree. This delta over kt, this one diverges. But this goes to 0, as t goes to 0. You are not convinced?
No, I'm still not convinced actually.
Okay, well, let's.
I can expand the exponential.
You cannot. Because at the t goes to 0 limit, that exponential is just, the exponent is not finite. You see, what you need to do is just x squared e to the power minus x limit as x goes to 0. X goes to infinity, sorry. This is the limit we have. Or if you like, this is the limit as y goes to 0, e to the power y over y squared. Now 1 over y squared. This is limit as y goes to 0, minus 1 over y squared, e to the power plus 1 over y squared divided by 2. No, this.
It's again 1 over y.
Now this it is 1 over y cubed. This is the limit as x goes to infinity of x squared over e to the power x. Now convinced?
Okay.
Okay. You see, just keep in mind, exponential just goes to zero or diverges faster than any polynomial. Whenever you have an exponent times the polynomial, it's the exponent that determines the asymptotic behavior. If it goes to zero or if it diverges. Okay, so this is the electronic part. Now let's look at the vibrations. Well, the vibrational modes, let's say the J vibe will be equal to sum over all the vibrational states of e to power minus beta epsilon y. Well, most of the time the temperature only the lower vibrational modes are excited. Because higher, you see, at this temperature, higher vibrational modes have epsilon is much larger than kT, or beta times epsilon vibrational for the large excitations. This will be quite a large number, so this term will be very small. So we can basically ignore their contribution. But if we ignore their contribution, for the lower vibrational modes, it's mainly harmonic. There won't be much deformation, so the system will be close to the ground state of their potential. So this will be approximately e to power minus beta, well, h bar omega, and well, let's just ignore the ground 0 point energy, h bar omega times n. Of course, n goes from 0 to a few. But again, for n large, there won't be any contribution. Since there won't be any contribution, this vibrational modes will be, I can just replace it by n0 to infinity. E to the power beta h bar omega n, or e to the power theta, no, minus to the power n, where this theta vibrational, this is just h bar omega over k. Well, this is just trivial to sum now. This is 1 over 1 minus e to the power minus theta vibrational over t. Well, we can now consider the various limits. Small temperature, or let's start with the large temperature limit. Large temperature meaning that theta vibrational, this is much less than 1. So this J is now approximately 1 over 1 minus theta over T, which is this, cancel this one, we have a plus T over theta V. Now we can calculate the contribution to the specific heat. You see, this is the contribution to the specific heat of this vibrational mode. this is equal to nk d over dt t squared. Well, the logarithm of j is just logarithm of t. If we take the derivative with respect to t, that is 1 over t. This is just equal to nk. Well, this was basically the classical result. You see, in the equipartition theorem, what does the equipartition theorem told us is that if your energy is a sum of the squares of certain expressions, then each one of these square terms would contribute k over 2 to the specific heat. So this harmonic oscillator is just, we have two terms. First, you can say that this is nk over 2 times 2. Now let's look at the small temperature limit. Well, small temperature just means theta v over t is much, much larger than 1. Well, if theta v over t is much larger than 1, well, let me just take this one. This is a small number. Well, this is approximately 1 plus e to power minus theta vibrational over t. And then we can just do the same thing that we did before. The logarithm of j is just the logarithm of 1 plus e to power minus theta vibrational over t. Take its derivative. This is the logarithm of, no, not the logarithm. If you take the derivative, this is 1 over t squared theta vibrational modes e to the power minus theta vibrational modes over t divided by 1 plus e to the power minus theta v over t. Or if we rewrite it, theta v over t squared times 1 over e to the power theta v over t plus 1. Now the specific heat, just multiply this by t squared and take the derivative once more. Due to the vibrational modes, this is nk. Well, if I multiply this by t squared, it just cancels this t squared over there. So I have theta v times the derivative with respect to temperature of 1 over e to the power theta v over t plus 1. And k theta v minus theta v over t squared. Now if I take the derivative, e to the power theta v over t divided by e to the power theta v over t plus 1 squared. And again, this just goes to 0 as t goes to 0. Now, basically, the expression we obtained over here is more or less the same thing that we obtained in the electronic part. But the difference from the electronic structure is that if you remember in the electronic structure, when we looked at the contribution to the CV, it had a peak somewhere when the temperature, the energy corresponding to the temperature was comparable to the energy splitting, if there is an endless splitting. And then it again went to 0. So at large temperature and small temperature limit, there is no contribution from the electronic structure. But in the case of the vibrational motions, due to the vibrational motion as a function of temperature, at small temperature there is no contribution, but at large temperature there is a contribution, and it goes to nk. So basically it will start to increase, and then asymptotically it will reach that value. So there is this transition between 0 contribution to some finite contribution. And then finally, there's the nuclear contribution. Now, first let's look at the rotation. Sorry. Well, J rotations will be just e to the power minus beta epsilon rotation. Now, if you consider the rotational Hamiltonian, the rotational Hamiltonian is nothing but L squared over 2I. So we just have this diatomic system. So there's a single I. And this, the Hamiltonian will be the energy, epsilon rotational energies will be just h bar squared L plus 1 over 2I. So JRT will be sum over all the rotational degree, rotational microstates of e to the power minus beta h bar squared L plus 1 over 2I. Now keep in mind that we are summing over all the microstates. The microstates have the quantum numbers of the microstates are L, and also there is the LZ quantum number. But there's no dependence, the energy doesn't depend on LZ, there's a degeneracy. So for each L, we have how many microstates? How many degenerate microstates? 12 plus 1. And L goes from 0 to infinity. Now let me define theta r. No, let us keep it that way. So again, we will look at two limiting cases. Large T. Well, large T in this case basically will mean that beta h bar squared over 2I is much less than 1. This is what we mean by the large temperature limit. But if this is the case, you see the splitting between two L values, the energy, the splitting in the energy will be very small. The contribution, sorry, not the energy, but the contribution from two nearby L values will be very small. And secondly, the most contribution in this case will be from larger L values. So which will add to the fact that the contributing terms will change smoothly. But that means we can just replace that sum by an integral. From 0 to infinity, 2L plus 1, e to the power minus beta h bar squared over 2I, L plus 1. So how do we take that integral?
It's because integral, we have to change the variance.
Well, there is an easier thing. Just take the derivative with respect to L. You see, here we have the L squared plus L. Its derivative is 2L plus 1. Well, of course, then there is the additional factors, which mean it to cancel minus 2I over beta h bar squared. Now the integral is trivial. E to the power minus beta h bar squared over 2I, L plus 1, L from 0 to infinity of minus 2I over beta h bar squared. L goes to infinity, no contribution. When L is equal to 0, the contribution is just 1. So this is 2I over beta h bar squared. Let me just define this as T over theta r, some kind of a rotational temperature, where this theta r is h bar squared over 2ik. You see, h bar squared over 2I is kind of like the quantum of rotational energy. If I divide it by k, I get some kind of a corresponding temperature. So theta r is that corresponding temperature. So large temperature basically means much larger than this theta r. Now we have the JR. What is the corresponding contribution to the specific heat? Well, here I have the derivative of the logarithm of J, which is just 1 over T. This is again NK. Again, makes sense. We are looking at a diatomic molecule here. Basically, it has only 2 rotations. It cannot rotate around its axis. There is no energy for rotations around its axis, but it can rotate around the 2 perpendicular axes to its axis. And each one of these contribute a quadratic term. So we have 2 of them, and each one contributes an NK over 2. Again, consistent with the equipartition theorem. Now let's look at the other limit. Well, I will not just go over the derivations in detail at small temperatures. Meaning T goes to 0, then the J rho. It is just 1 plus 3 e to the power minus 3 theta r over T. It's just like the previous cases. You can just from here obtain the C specific heat, contribution to the specific heat due to rotation. And then you will see that this is just proportional to e to the power, let's say 3 theta r over T divided by e to the power 3 theta r over T plus 3 squared with a proportionality constant theta r over T squared probably. But nevertheless, at small temperature it again goes to 0. So now we see, at least up to this point, we have the, well, let's also look at the nuclear contribution. Well, by nuclear contribution, we mainly mean the various orientations of the spins. So Jn would be just 2sa plus 1. These many spin orientations that a molecule, a atom can have, and 2sp plus 1. So basically, there is no, since it's just a constant, it will shift the energy, the chemical potential, etc., but it will not contribute to the specific heat. So when we look at the specific heat, we basically now see that we have two temperature scales. One is the theta R, which is of the order of 100 Kelvin, and then theta V, which is typically of the order of 1000 Kelvin. At very low temperatures, neither the electronic nor rotational nor vibrational motions contribute to the specific heat. So it's just a translational motion of the atoms, which is a 3 NK over 2. Then we have the rotational temperature and the vibrational temperature over here. Once the temperature is in between these two temperatures, the specific heat will be, there will be an additional contribution due to rotations, which is just Nk, so specific heat should become 5 Nk over 2. And then when the temperature is even larger than theta V, the specific heat will start receiving contributions from these vibrational degrees of freedom, and then it will be 7 Nk over 2. So it starts from 3 Nk over 2, then around when the rotational degrees of freedom start to get excited, it makes a jump to 5 Nk over 2, then stays there, And then it makes another jump when the vibrational degrees of freedom starts to get excited. And it jumps to 7 nk over 2. Well, if you keep increasing the temperature, the vibrational modes will start to get overexcited, the molecules, or you just get the molecule will just break up. So this description will break down anyway. So you have to take into account various split up molecules also. So what is usually said is that, for example, if you are lower than this temperature, much lower than this temperature, what is said is that the vibrational degrees of freedom are frozen out. You only get the rotational degrees of freedom and the translational degrees of freedom. And then if you go below the temperature for below theta r, then the rotational degrees of freedom also freeze out. So basically what happens is, why the molecules start to rotate to start with? Basically, due to their collisions, they can just cause each other to rotate. But rotation is a discrete process. So they should get a minimum amount of energy to be able to start rotating. And this energy should come from their kinetic energy. But the kinetic energy of the molecule is determined by kT. If kT is low enough, then the translational motion doesn't have, this collision doesn't have enough energy to cause the molecules to rotate. So the molecules, they just don't rotate. And let's say if you start from a high temperature, but the atoms are already rotating, as you lower the temperature, well, this rotation energy will be transferred to the translational motion. Once the equilibrium is reached, of course. And so eventually, all the rotational energy will be transferred to the translational energy, and again, you get no rotation. The same holds for vibrations. Now, let's look at what happens when we go to the homonuclear, monoatomic. Or mononuclear. Now you see, the main difference from the previous treatment will be how we treat the nuclear states, nuclear and spin. So we need to evaluate J nuclear and rotational together. We will again assume that the spins, the interaction, the splitting due to the spins is negligible compared to the temperature. That's still an assumption we will make. So this is the energies will still, of the microstates, will still be given by h bar squared L plus 1 over I 2I. The energy states are still given by this number. But now the problem is, what is the corresponding degeneracy for a given L value? Now keep in mind that we have a two nuclear, two particle system. Which will be the product of spin times the spatial component, and this has to be under the exchange of the two identical particles, either plus or minus 1, since they are either fermions or bosons. So this is what we need to take into account. Now let's look at the spin wave functions of this system. How do you add the spins? So we have SA and SA. The maximum spin of the combined system if you just consider two spins, the maximum spin you can obtain is twice SA. Then you can have 2SA, one less spin. You can have a total spin 1 or a total spin 0. Now, which ones are symmetric, which ones are anti-symmetric? Let's do an example, an explicit example of spin 1. No, an even simpler example. Hydrogen. This is the relevant case for the hydrogen. Total spin 1, its set can be 1. This state is spin up, spin up. Total spin 1, its set is 0. This is 1 over square root of 2. Spin up, spin down, plus spin down, spin up. Total spin 1, its z is equal to minus 1. This is spin down, spin down. And then we have the total spin 1, its z is equal to 0 state, which is 1 over square root of 2, spin up, spin down, minus spin down, spin up.
S is equal to 0.
S is equal to 0, right? Well, you see, this is symmetric under the exchange of the spins. The other one is anti-symmetric. And also note that all of these states in a given multiplet are symmetric, because the spin raising and lowering doesn't change the symmetry. Spin raising and lowering operators are symmetric themselves, so they don't change the symmetric property of the state that they are acting. If you start with a symmetric state by lowering the spin, you still obtain symmetric states. This is in general true. The highest weight, this one is symmetric, 2SA, this is symmetric. This is anti-symmetric. This will be symmetric, etc. One is symmetric, one is anti-symmetric. It will always go on like that. So if you want to obtain the number of symmetric states, okay, so this is one thing about the symmetry of the spins. Let's just say an S is the number of symmetric spin states and an A is the number of anti-symmetric. Spin states. Now, if we go back to our partition function, if you go back to our wave function, let's look at the case when we are considering fermions. The total wave function should be anti-symmetric. I have two possible cases. Either the spin is symmetric, special part is anti-symmetric, or spin is anti-symmetric, the special part is symmetric. Now the special part, space component, its symmetry is determined by the L. If I just exchange the two particles, I just get a minus 1 to the power L. So if I have a fermionic nuclei, the wave function should be still the product of spin, symmetric, special, antisymmetric. Well, let me put the L also over here. Or spin antisymmetric, spatial part symmetric. I have these two possibilities for the microstates. J will be, well, I have L. If the spatial part is antisymmetric, that just means I'm summing over L odd. Of course, the microstate is determined by the spatial wave function and the spin wave function. The spin doesn't contribute to the overall energy. So I need to multiply this by 2L plus 1 e to power minus theta r over t L plus 1. And then I just need to multiply this by the number of, okay, this is odd, so this is number of symmetric spins, spin contributions. No, there's no L, sorry. Plus, I have L, 0, 2, etc. Then I'm looking at the second kind of microstates where the spatial part is symmetric, so the angular momentum is even. Again, 2L plus 1 e to the power minus theta r over t L plus 1. And now I need to multiply the number of antisymmetric spin states. Which I can write. This is for nucleons satisfying the Fermi-Dirac. This is NS R odd plus NA R even. Where here R odd is the sum over odd L values of 2L plus 1 e to power minus theta r over t L plus 1, and R even is the sum over even L values. So basically the first thing we need to do is to determine these NS and NA values. That's the first thing we have to do. Now we had this, okay, the spin SA, another spin SA, the total spin could be 2SA plus 1, plus 0. How many symmetric combinations can we form from two spins? Well, let's see. Basically, we have these two numbers, S1 and S2. It has various coefficients. Now the total state, let's look at this way. Let's try to construct a total spin, a symmetric one, whatever the Z is. So this will be equal to spin of the one, spin of the second one, multiplied with certain coefficients, summed over S1 and S2. Okay, so this is a matrix. And if it is symmetric, CS1, S2 should be symmetric. And similarly, if we were looking for the asymmetric one, this should be asymmetric. So how many, so this is a, C is a 2SA plus 1 times 2SA plus 1 matrix. If it is symmetric, how many independent parameters it has? Let's look at a symmetric matrix. N by N. Asymmetric matrix. Since it's anti-symmetric, the diagonals are all zeros. And whatever we have over here, we have minus A on the other side. So the independent parameters are just above the diagonal. You can just choose them to be above the diagonal. So how many of them are there?
N times N minus.
Well, in total we have n squared elements. If I remove the diagonal, this many elements remains. I'm just taking half of it. So the symmetric ones, no, asymmetric ones, sorry, and A is actually 1 over 2 times 2SA plus 1 times 2SA plus 1 minus 1. So this cancels this one, this cancels this one. So we have this many anti-symmetric spin wave functions. What about the symmetric ones? Well, the total of the anti-symmetric and the symmetric wave functions should be just 2SA plus 1 times 2SA plus 1. So for Fermi-Dirac, if we have a symmetric wave function, the spin degeneracy is this much. Then we have to multiply with an anti-symmetric special wave function, so the sum over their contribution is RO. And if we have an anti-symmetric spin wave function, then we multiply with R even. For the Bose-Einstein, that's basically the other way around. So if we have a symmetric spin, we have to multiply with symmetric special wave function. If we have an anti-symmetric spin, so this gives us what J is. Now let's look at certain limiting cases. Let's start with large temperature. What happens in large temperature? Well, if you look at the R odd and R even, when the temperature is large, well, these are all close to zero. Now let's see. Okay, when the temperature is large, basically we can replace both of them by their integrals. When the so basically what will happen is this R odd will be equal to R even, approximately equal to. Well, basically different L values will not really change the, if you just change L by 1, the contribution will not really change significantly. Well, our odd is R even, so these will be approximately, each one is just L from 0 to infinity, 2L plus 1, e to the power minus theta R over T, L plus 1. Half of these. Because our odd just contains half of the terms, or even contains the other half. But this is nothing but the classical result, or the heteronuclear case. This is theta r over 2t. So both the, well, if you go back, J, now these ones are equal, so I can just take them into common parentheses, Bose-Einstein, or whether they are satisfy the Fermi-Dirac case. They will both be 2sa plus 1 squared theta r over t times 1 over 2. Well, if you compare with 2sa plus 1, 2sb plus 1, these are the nuclear spins, and then we had the theta r over 2t. The difference is just a factor 1/2. Well, this is kind of expected, because if you consider this diatomic molecule, when we are in the classical limit, when we are obtaining the partition function, we are summing over all the possible configurations, which will also include all the possible orientations of my molecule. But let's say if we take this as our z-axis, then we will have an integral over phi, but changing phi from 0 to pi will not give me a new orientation of my molecule, it's just the same state. Whether the two A's are like this or they are like this will not give me a new state. So instead of integrating from 0 to 2 pi, I should integrate from 0 to pi, which is, since the energies do not really depend on phi, so this is 1 over 2, 0 to pi d phi. This is the origin of this factor 1 over 2. Well, the other limit will be the small t limit. L plus 1 e to power minus theta over theta r over t, L plus 1. Well, basically, we just keep the lowest term. In this case, L is equal to 0 will be just 1. If you like to keep the next one, 1 plus 3 e to power minus theta r over t times 2. And our odd, no, sorry, this is L is equal to 2 term is just 6. Our odd, which is L from, again, 2L plus 1, which is approximately, no, this is 1, 3. It is just 3 e to power minus theta r over t. Now this term is also negligible. Because since we are at a small temperature, theta r over t is a huge number, so e to the power minus theta r over t is itself a huge number. It's a negligible, it's a very small number, so its sixth power is even more negligible. And well, the derivation is more or less the same from this point on. Now there's some definitions, let's say ortho and para. You see, if you look at, for example, the hydrogen, the nuclears are spin 1. The spin 1, the total hydrogen nuclear state can be spin 3, the nucleons are protons, they are spin 1, the total spin can be at most 1. If the spins of the hydrogen are in total spin 1 configuration, is called orthohelium. If it is in spin 0, it's the parahelium. Parahydrogen, sorry. Now, in general, the ortho is used for the combination with the larger weight, larger statistical weight. Now, what does it mean, larger statistical weight? Well, if you look at our expressions over here, this is larger than this one. That is basically, the first term is called the ortho, the second term is called the para, whatever the system is. It can be odd L or even L, depending on whether the nuclei is a fermion or a boson. Now, so what you can actually do is, okay, just take some system. It can be the hydrogen, for example, hydrogen molecule, and study the specific heats at high temperature, at low temperatures. And you will get some predictions from here, and the predictions do not match the experiment. So that's kind of one problem. At least at first it was one kind of a problem. So the specific heats that we obtained from this one at low temperature didn't match the specific heat that we measured at low temperature. And we know the explanation now. So basically, how do you create your system at low temperature? You start from some high temperature. In high temperature, you have some distribution of the ortho and the para molecules, and then you lower the temperature. Well, you lower the temperature in, how long does it take? Well, it depends on the system, but let's say hours. You see, does your system keep equilibrium if you cool your system within an hour? Well, since we are talking over here about the nuclear spins, nuclear wave functions, and it turns out that the nuclear state, the relaxation time of the nuclear state is much longer than the cooling time. So basically, the nuclei are not in thermal equilibrium when we created this experimental system. So we had to wait much longer to obtain the predictions from the specific heat, from this theoretical treatment. And when they did it, it actually worked. So that's just a kind of a warning about the relaxation times. Now, any questions here? Well, I don't want to go into all these details because the derivation is mainly more or less the same. The important thing is how do you interpret the result. There's just one more subject I would like to finish today. So that's why I'm just kind of jumping the results. Now, any questions?
When we are talking about rotation, we treat the system like an atom instead of molecules. We say that the rotational angular momentum is, let's say, L squared is L times L plus 1 times h bar square, right?
Mm-hmm.
How can we say that?
I'm not really treating it as an atom. I'm just saying that, okay, so I have these two nuclei. Okay, if you have a two-particle system, what you can do is you can always make a change of variables. One variable will be the center of mass motion, which we are already treating it. So it's just this V over lambda cubed factor. And the other one will be just a single particle motion. And that single particle has an angular momentum M. So that's what I'm doing over here. So L is still the total angular momentum, and the energy corresponding to this L will still be L squared over 2I. No, here basically I'm using that one. The rotational motion of the nuclei, you see, before I was treating the rotational motion of the spins. I'm just treating it separately. This is the rotational motion of the nuclei. And then, okay, besides this, you can basically just generalize this to more than 2 atoms. You have multi-atomic molecules. Well, the thing, I mean, if you look at the vibrational degrees of, the rotational degrees of freedom will still be the same. There's not really much modification. The vibrational degrees of freedom, well, there will be many different vibrational modes with different frequencies. That is something that needs to be taken into account. Not here, when we were looking at the vibrational degrees of freedom, we just had a single frequency. But when we have a multidimensional, multi-atomic molecule, we will have many vibrational frequencies. But at the end of the day, if you just take these variations into account, the algorithm, let's say, is more or less the same. How many vibrational degrees of freedom an N molecular atom has?
N molecular.
N vibration. Should depend on the formation of the molecule.
Well, in general, except on special cases like a linear molecule, etc. We have in total 3 N degrees of freedom. Among these 3 N degrees of freedom, three are translational degrees of freedom. Three are rotational degrees of freedom. And the rest will be the vibrational degrees of freedom. And keep in mind that the Hamiltonian for the rotational degrees of freedom will not be equal to L squared over 2I. Do you remember the expression?
I think that you're right as a theta.
I think it should be L I inverse L. Just check. It should be this one. You see, when we are writing H is equal to L squared over 2I, we are assuming that I is I0. This is the case for a diatomic molecule. And you just choose one of your axes to be along the molecule, and the other 2 axes are perpendicular to it. So if you just, within those axes, the moment of inertia tensor is given by that matrix. And if that is our matrix, then the rotational Hamiltonian is just L squared over 2I. But if you have a complicated object, let's say, then the rotational Hamiltonian is just not L squared over 2I. Well, let me just put some vector signs. Yes, you have a question.
Okay. No, no.
Okay, in our remaining time, let's just discuss a bit about the chemical reactions. Now, up to here, we have been already dealing with ideal gases, but let's look at chemical reactions. What can we say about chemical reactions? Well, let's look at a reaction where some number of A molecules or atoms, let's say, combine with some other number of B molecules, and they form some number of X molecules and some number of Y molecules. Molecules or atoms, I'm not really making any assumption about that. So what can we say about the equilibrium? Now, I will assume that this is at fixed temperature and pressure. Now, this is the most realistic case. When you mix chemicals, you, in general, do it in an open container, and that open container means that the pressure is constant. It's the atmospheric pressure. And you again, quite often do it at constant temperature, the atmospheric temperature, most of the time. If you remember your chemistry courses, that's what you basically did. Now, first of all, let's look at the Gibbs free energy. This was defined as E minus Ts plus PV. And the differential of the Gibbs free energy, if you just remember the thermodynamic relationships, this is minus SdT plus VdP plus mu dN. You see, since we are looking at the processes that happen at constant temperature and constant pressure, these two terms are constant. But Gibbs free energy, and when equilibrium is reached, N also doesn't change, so dG is 0 in equilibrium. So in equilibrium, G is a maximum. Well, G is an extremum. Is it a maximum or the minimum? Well, I mean, let me just cheat slightly. The formal derivation is a bit more involved. But you see, in equilibrium, S is a maximum. So this S in G appears with a minus sign, so G is a minimum in equilibrium. If the processes happen at constant temperature and pressure, then in equilibrium G becomes a minimum. Now again, G in this form is written as a function of temperature, pressure, and the number of particles. And it's an extensive property. So the only extensive parameter it depends on is N. So G has to be proportional to N. And the proportionality constant is just the chemical potential as a function of temperature and pressure. I can say this just using the property that the G is an extensive parameter. So let us look at this, go back to our reaction first. Let's assume that any reactions occur spontaneously. Now the number of A particles change by minus nu A times N, delta N, sorry. This is the change in the A particles. The change in the B particles is just nu B times delta N. The change in the number of X particles is plus nu X times delta N. And the change in the Y particles is plus nu Y times delta N. Well, the change in the Gibbs free energy of the system is, well, mu A times delta NA basically look at over here. The change in the Gibbs free energy at constant temperature and pressure is just mu times dN plus mu B delta NB plus mu X delta NX plus this is X mu Y delta NY, which is minus mu A minus mu B plus mu X plus mu Y times delta N, and this should be equal to 0 in equilibrium. So we have our first relation, mu A plus mu B, this should be equal to mu X plus mu Y. Now, what is the chemical potential? Well, if I forgot to bring the, let me see if I can find it, the expression. Now we can just assume that the reaction is happening in a gas form, or we can just assume that it's very diluted. So we can use the expression for the ideal gas. Yes, this is the Helmholtz free energy. A is an epsilon. Epsilon is due to the internal energy, this minimum energy configuration, and plus nkt logarithm of n over v lambda cube, lambda to lambda cube, minus nkt logarithm of j. This is A. And mu is nothing but dA by dN. So we can calculate the mu. This is epsilon plus kt logarithm of n over v lambda cube plus kt minus kt minus kt logarithm of j. So let's cancel this one. Let's see, this is mu is equal to some mu 0, which depends on temperature. In this mu 0, I include the epsilon, the j's, all of that, plus kt logarithm of n lambda cube. This is true for A, for B, for X, and for Y. Well, I know that now mu, I just put it over here. So let's see what I will get then. Nu A times mu 0A plus nu B, mu 0B minus nu X, mu 0X this is x minus nu y, mu 0 y. Now these mu 0, okay, epsilon is an internal property of the molecule. And this J is an internal property of them. This is just a constant. This is an internal property. It just depends on the temperature. Some number that depends on the temperature. Plus KT times logarithm of lambda depends on the, let me rewrite it slightly differently. You see, lambda depends on the temperature also, and also depends on the type of, the mass of the particle. It doesn't depend on the density of the particle. So let me also include this lambda over here in mu 0. And of course, I cannot just talk about the logarithm of n. I have to put some reference n, and it's dimensional. So I can write mu in this form for all the particles. N0 is just some reference number density. And let me, again, for simplicity, just define this ratio and A over N0, denoted by A, etc. Similar for B, X, and Y. So here I will get logarithm of, you see, I'm just putting it over here. And I'm moving everything to the left. A to the power nu A. B to the power nu B. Divided by X to the power nu X. Y to the power nu Y. This should be equal to 0 in equilibrium. Well, this just tells me that this ratio should be a function of temperature only. Well, okay, a function of temperature only, a function of temperature only. One thing, it doesn't depend on the rate of the chemical process. It can be very fast, it can be very slow. Or if you put a catalyst in your system, what does a catalyst do is, if you have such a chemical reaction, if some catalyst enters into this reaction on the left, it also appears on the right in equal amounts. So this reaction again is not modified, and hence this ratio is not modified. The catalyst doesn't change this ratio. Or the initial concentration of A, B, X, or Y doesn't change this ratio. So this is a function of temperature only, and this is the condition of equilibrium for this chemical reaction. Do you remember Le Chatelier principle from your chemistry? Okay, I have a hard time pronouncing it. Chemistry 101. What was your chemistry grade? Do you remember?
It was something like BA or B.
Okay. Well, this principle basically states that, let's say, if you have such a chemical reaction, this one, and you there's an external influence, like let's say you increase the amount of A molecules in the system. The system will behave in such a way as to reduce the effect of that external modification. So basically, if this system is in equilibrium, and then you add some A molecules, there will be some B molecules, this reaction will move in the forward direction. So some of this additional A and B molecules will be converted into X and Y molecules. That's basically the principle. Well, at this, the application of that principle in this form, you can see over here. You see, let's say the system reaches equilibrium. So this ratio is equal to KT. Then you add some more A particles to here. So you lower this ratio. But this ratio, when equilibrium is reached, is determined by the temperature only. So if you lower this ratio, when the system reaches equilibrium again, this ratio should be back to its initial value. But since you lower this ratio by increasing A, so the system will lower A and also B and increase X and Y. So, and eventually in equilibrium, the system will reach the same ratio. Well, you can drive the same result also if you like from the microcanonical ensemble in an isolated system. But of course, in an isolated system, you have to keep in mind that such a reaction can be endothermic or exothermic. So there might be some energy released or energy absorbed due to this reaction. So you also need to take that into account, because the total energy will not be constant. Total kinetic energy will not be constant, let's say. Yes, questions? Okay, so then see you tomorrow.